let's take a look at Oersted's discovery. This is textbook section 12.2 if you want to take a look afterwards. The question that we're going to answer right now is there a relationship between electricity and magnetism? We all know what a magnet is. A magnet applies a force on metal objects. It allows us to hang things on our fridges. It applies a force on other metals. Electricity is how we do all sorts of things. It's moving electrons. Now, how are the two related? Like I said in the previous video, Oersted was the first to figure this out, and it's funny because he figured it out by accident. He didn't mean for this to happen. He was actually trying to prove that the two are not related. But then he ended up proving that they are related, and this started a whole field of new study back in the day. So let's watch a couple videos to help us understand, and then I will summarize the videos for you. So when you watch the videos, you don't have to take notes, just watch. You will take notes on my summary of the videos.
The source of that magnetism was betrayed years ago, more than 150 years ago, by a fellow by the name of Hans Christian Oersted, who was a professor type teaching, I believe he was in a high school classroom. And he was showing the students that there's no relationship between magnetism and electricity. The physics books at that time had electricity as one subject and magnetism as another. And Oersted was showing there's no relationship between the two. And one of the things he would do is he would line up the piece of wire like this and put it over a magnet, pass a current through it, and you really don't see anything happening. There's no interaction. But after class, a student came up and held the wire in this direction, and when a current passed through it, okay, watch this, when a current is passed over the wire like this, boom, you see that interaction? It turns out there is an interaction between a current carrying wire and a magnet. And it turns out, to make a long story short, the source of all magnetism is moving electric charges. And when the charges move through the wire, they set up about the wire a magnetic field. And that magnetic field is in concentric loops around the wire. If I pass this wire through a hole in a piece of paper, and I put a whole lot of little compasses around the wire, and no current goes through, all those compasses would point north. But you know what would happen if I put a current through that wire? Bam! All the compasses will line up with the field. And it turns out that field takes the shape of concentric circles about the wire. The further away you get, the weaker they get, but the direction is all that way. So surrounding every current-carrying wire is a magnetic field that takes the direction of the concentric circles.
Let's watch one more video to show us that again, and then I'll summarize.
In 1820, Danish physicist and chemist Hans Christian Oersted was setting up materials for a lecture. His materials included an early kind of battery called a voltaic pile, constructed of copper and zinc plates in a dilute acid solution, and a wire held in place here by a set of clamps. Oersted and other scientists of his day knew that when a wire was connected between the positive and negative terminals of a battery, electricity would flow through that wire. Electrons actually move from negative to positive. However, the convention is to think of electrical currents as moving from positive to negative. So that's how we'll show it here, using red particles. Back then, scientists still had much to learn about electricity. Preparing for his lecture, Oersted made a very important discovery about the phenomenon, quite accidentally. Among Oersted's scientific paraphernalia was a compass. Its needle, of course, pointed north in alignment with the Earth's magnetic field. Oersted happened to place the compass near his battery and was startled to notice that the compass needle moved. As Oersted deduced, this happened because the wire produced a magnetic field around it when it carried a current. If there is no current in the wire, the needle reverts to the alignment with the Earth's magnetic field. As it turns out, an electric current, made up of moving charged particles, produces a magnetic field that circles around the moving current. as shown by these blue lines. If you reverse the direction of the current, then the magnetic field around the wire moves in the opposite direction, and the needle on the compass flips to reflect the change in field. If you move the compass to a new spot near the wire, the needle will realign with the direction of the magnetic field in that particular location. Oersted's accidental discovery was solid evidence that electricity and magnetism were related phenomena. The announcement of his findings incited a tremendous outbreak of research in the nascent field of electromagnetics in the early 1820s.
All right, let's summarize this. This is where you have to take some notes. Oersted's principle was exactly what the video says. So what the video told us was that Oersted discovered, I'm going to backtrack a little bit. I don't know if you noticed, but the two videos had slightly different theories as to how this occurred, this discovery of Oersted. The first video said that a student came up to Oersted after his lecture, that he was teaching, he was lecturing, and a student came up to him after, and they by accident figured out this theory. The second video said that Oersted figured it out before his lecture. So it seems like it was definitely figured out by accident at a lecture of Oersted's because he was a professor. But it's funny because the stories are slightly different. So I guess history is a little bit unclear as to exactly how this happened. We do know that Oersted was the one that figured this out. What did he figure out? If I have a battery, oh my goodness, my laptop is having a hard time. There we go. Negative, positive terminal. And I connect a wire to it, a conductor. What happens? Well, current is going to flow. Current flows from positive to negative, right? That's conventional current. We're talking about conventional current here, not electron flow. Remember, conventional current goes from positive to negative. If that happens, when you have current through a wire, that current produces a magnetic field. So now, current is producing a magnetic field, which is crazy. All you need is a wire to make a magnetic field, to make a magnet. So technically, when you plug your devices in, like your laptop, your phones into the wall, the wire that you're using to plug into the wall has a very little magnetic field in it. Magnetic field is quite little, but it's there. So a wire creates a magnetic field, and this magnetic field will point in circles around the wire. So it points in circles around the wire, like this. And the direction of the magnetic field matters. We'll talk about that in a minute. So this is Oersted's principle. Write this down, please. Pause and write this down. Whenever charges move through a straight conductor, so we're talking about a straight wire here, not coiled up, but straight. So whenever charges move through a straight conductor, a circular magnetic field is produced, pointing in circles around the conductor. So pointing in circles around the conductor. The direction of the field depends on the direction of the current. All right. What am I talking about here? So let me show you what I mean. If I have a wire, so here's a wire. I'm going to draw it kind of like 3D. Here's a wire with current flowing through it this way. So here I have a positive terminal, here I have a negative terminal. If the current is flowing to the right, that will create a magnetic field in circles around the wire, and it will point this way. I'll tell you how I know that in a second. What if I reverse the current? What if the current instead points to the left? If the current instead points to the left, so I have the positive terminal here, and the negative terminal here, and the current is going from positive to negative through the wire, the magnetic field lines will still point in circles, but look, they'll point the opposite way. It'll be curling around the wire in the opposite direction, these magnetic field lines. How did I know that? Well, what we do is we use something called the right hand rule for a straight conductor. You're going to be using your right hand to help you remember how the current and the magnetic field lines, how they're related. Here's what I'm talking about. So here is a straight wire, like this, straight wire, and the current in the straight wire is going to the right. Take your right hand, and you cannot use your left hand because it'll be backwards. You have to use your right hand. So right now, take your right hand and point your thumb to the right, just like this. See how the thumb is pointing to the right? The thumb lines up with the electric current. So the current I is pointing to the right, and your thumb points to the right. Notice you can curl your fingers in circles now. Notice here, like this, your fingers are coiling up in a circle. The way your fingers curl up is in the direction of the magnetic field. So the magnetic field is in circles, like this, around the wire. And notice your fingers point down in front of the wire, and they point back up behind the wire. So imagine you were like grabbing, if you were grabbing that wire, your fingers curl down in front of the wire and they curl up behind the wire. So you kind of draw these lines in the direction of the way your fingers curl, like this. I'm going to do some examples to help us understand this. I feel like I maybe found a video for this. Yes, here it is. Let's watch a quick video to help us see this.
Hand in that symbol and say that the thumb points in the direction of the current, then the magnetic field is going to curl around in the direction that our hand is curling, like that. The curl right hand rule also works in reverse. If we have a current...
Okay, we're going to stop there because that's going to get confusing. Okay, so this is a right hand rule for a straight conductor. Again, your thumb is the direction of the current. Your four fingers curl in the direction of the field lines. So the field lines point in circles, the current points straight. Remember, the symbol for current is I. Do you remember that? The symbol for current is I. The symbol for a magnetic field is B. Whoops. So sometimes you'll see this B. That means magnetic field. All right, so the B or magnetic field lines go in circles around the straight wire. Let's try some examples. So what if I have a wire going up, like this, up and down, like this? The positive terminal is here, the negative terminal is here. Draw that for me. Which way is the current through the wire going? From positive to negative. So the current is pointing up. We'll label it as I. Now take your right hand and figure out the magnetic field. Which way will it point? How do we draw a magnetic field? What I do is I always start from the back and curl at the front. And then notice I don't have them at the meet because it's at the back. It's behind the wire. So I only draw in front of the wire, over the wire. Behind the wire, I don't draw the field lines behind the wire. And you can draw another circle like this because the magnetic field is down the whole wire in circles around it. So now, which way should I draw arrows on these circles? Should I draw them counterclockwise? Or the other way, should I draw them clockwise? Which way are the field lines pointing in circles? So what you do is you take your right hand and point your thumb straight up to line up with the current. And then which way are your fingers curling? Pretend you're grabbing that wire. If you're grabbing that wire, I always think, okay, in front of the wire, my fingers point to the right. So in front of the wire, my fingers point to the right. And then it curls, and behind the wire, my fingers point to the left. That's the way it's curling. It's curling this way. That's the way my fingers are curling. Okay, what about if the wire is still up and down, but my positive terminal is here and my negative terminal is here. Which way is the current pointing? Conventional current points from positive to negative. So the current is pointing down now. So my thumb will point down. And notice your fingers are curling in circles. If you're pretending that you're grabbing that wire, which way is the field pointing? So I start from behind, coil in front, and it goes back. From behind, curl in front and back. From behind, curl in front and back. Now, which direction am I drawing the arrows on? So if my thumb points down and my fingers are curling, so I'm literally doing this right now as I'm speaking. I'm pointing my thumb downwards, like towards the ground, and my fingers are curling. And if I'm grabbing that wire, my fingers are curling left behind the wire, like this, and they curl up and to the, sorry, oh my god, I have my directions all wrong, to the right, and then they curl and go left in front of the wire. So again, if my fingers are curling, they curl to the left in front of the wire and they curl around. So pretty much just follow the direction of the way your fingers, your four fingers are curling. If I were to draw this, so my thumb is pointing down with the current, and my fingers are curling 2, 3, 4. Geez, this is a hard thing to draw. My fingers are curling this way. You see that? My thumb is pointing down with the current, and my fingers are curling this way. So this is the way that I draw the magnetic field, is this way, around the wire. All right, now we talked about, okay, if the current is, we drew this here, to the right, try to now use your right hand. Try to see if my directions make sense here. If my thumb points to the right, then did I curl the magnetic field properly? This is the magnetic field here, B. And this is the current, I, to the right. The current to the left here. The magnetic field is curling this way, B. Now, we did up and down current. We did left and right current. Now, what about if the current is, what if I have a wire like this? There's one more scenario we're going to go through. This is a wire. Let's say you're looking into the wire. You're looking like inside of it. Okay? So it's not going left and right. It's not going up and down, but it's going into or out of the page. Let's say the current is pointing into the page. So it's going away from you. This is kind of weird to think about, but it'll make sense once we do some practice. So the wire is not going to the right or left. The wire is not going up or down, but it's going like into the page, away from you, into the page. So like into your laptop, the wire is coming into or out of the laptop, and the current is going into the page here. How do I show current going into the page? Okay, have any of you ever done archery before, where you have like a bow and arrow, and you shoot a bow and arrow, right? So if you look at the arrow itself, the arrow at the back has a feather, at the front has an arrow, right? Imagine if this arrow was coming at your face. I know that's a really horrible thing to imagine, but imagine by accident somebody shoots this arrow at your face. I'm sorry, this is really horrible, but it'll make sense why I'm saying this. If an arrow is coming at you, all you're going to see is the tip of the arrow. So all you're going to see is a dot. You're going to see a dot if the arrow is coming towards you. What if you shoot the arrow away from you? All you're going to see is this back thing like this. So if the arrow is going away from you, you're going to see an X, the back of the actual, it's like a feather at the back. So if the arrow is going away from you, you're going to see the back of it, X. That's the same thing with current. If the current is going into the page, so it's going into the computer away from you, then you're going to see an X. That's the current going away from you. What if you have a wire and the current is coming out at your face towards you? You're going to see a dot. This is current coming out. Oh my God, what's up with my laptop? Current coming out of the computer towards you. If this is the case, how will the magnetic field lines point? This is kind of weird to think about. Just get the general idea, but it's okay if it's a bit confusing at first. Don't worry. I'll refer you to some textbook pages to help you understand this as well. So let's talk about this. If I have a wire going into the page like this, into the page, and the current is going into the page, so like this. Current is going into the page. That's an X. How will the magnetic field lines point? Magnetic field is in circles around a wire. So again, point your thumb. Now the current is going into the laptop. So I literally jab my thumb into my laptop and I see which way my fingers curl around it. So if I jab my thumb away from myself into the laptop, magnetic field points in circles and my fingers are curling clockwise like this. So if I have a wire with current going into the laptop, then the magnetic field lines are pointing in circles around. And then as I'm going to erase this to make some space. As you get farther and farther away from the wire, the field lines become weaker and weaker and weaker. So we draw the lines farther and farther away from each other. And I don't know, I'm sorry, my laptop is not responding to me very well today, but we'll do our best. I think my laptop is over online learning as well. It just doesn't want to anymore. Now, what if the current isn't, instead of going into the laptop, what if the current is coming out? So I have a wire and the current is coming up towards your face. So literally point your thumb out towards your nose. Point your thumb towards your nose, like out into your face. Then curl your fingers around the thumb. The fingers are curling around like this. That's the magnetic field. And it's pointing, you notice it's pointing counterclockwise. There you go. Okay, and the lines will get farther and farther away because the magnetic field is getting weaker and weaker and weaker as you get farther away from that wire. Remember, this circle here is a wire with current flowing through it. These big circles in green are the magnetic field lines. So if I bring a paper clip close to this wire, paper clip will feel a force towards the wire because the wire isn't producing these magnetic fields here. Okay? Let's see, what else do I have to tell you? Is that it? I think that's it. And now you're going to try some practice in the textbook for me. All right.